Of course, also water pipes. Water pipes are very important. Water quality and water loss are massive. So much water in the world is wasted by pipes, so we want to put robots into pipes to inspect them and to repair them. We're building robots to do that, such as this robot here. But pipes are quite difficult. They have weird bends, weird twists. So the Egypt robot couldn't do that. A much more complicated robot, it has 12 different things that change length. So in this case here, we're climbing the shaft, or climbing a pipe, and we're twisting. That means we can twist, we can choose. So you approach a T-junction, do you go left, do you go right? We can choose to go left or to go right in that environment there. Another thing, if the pipes are metal, which many of them are, certainly in gas pipes, you can have metal robots. So small robots, it can climb, in this case go around a square box, square being harder than circular, but it can just drive around and inspect and measure. Let me show that again. So the really difficult thing is, though, you saw it go from the flat to the upright. It looks really, really easy. In fact, it's really, really hard, because what happens is either your wheel's stuck to the bottom or it can't grip to the top. So it's very hard to get that transition between things. So I'll show you it again. So and also that way, and also going up. Very, very difficult. This point here is very, very hard. It sticks here. How do you get it to do that? It looks easy. It really isn't easy. And likewise, this point here, going from this point to this point here is really hard. It might fall off. How do you manage to do that? So I think many things that look easy are really good because it looks simple, because it works really, really well. We're also working a lot on how you power these robots. So I've shown you a small robot there. Wouldn't it be great to do robots that could inspect things such as aircraft engines? So we have aircraft engine, difficult to get through the blades to the back, for example. Let's put in 50, 100 small robots to go inside there and inspect. The real problem with robots that are quite small is the power. How do you get the power to them robots? Batteries aren't that good yet. So we have stuff we're doing right now which can actually fire microwave energy, very, very high powerful energy at robots. The robots can harvest that energy, capture it, and they can power themselves. The downside here is the energy is very, very dangerous. You couldn't do it here, it would kill you all. Really, really bad. But if you've got an aircraft engine in a controlled environment, you could do it. So we're working on that. So you have robots with an aircraft engine, a massive transmitter, and they can drive around, they can inspect, and they can measure things. And that's very important for small robots, because small robots, mostly we can make them very, very hard, but powering them without wires is really, really, really hard. So I'm going to the last case now. So I've been through different cases. I've been through the open spaces, been through these enclosed pipes. I want to talk about a really, I guess, a specialised case. This case is really about restricted access. So you want to enter a structure, a building, through a small space. On the other side, though, it's very big. So this room here, for example, you want to get into this room through a small drilled hole. Once you get through, you want to explore this space here. So how can you do that? And that's what we're working on. So for example, we've got a house here. You want to get through a small hole here and inspect. Many people say to me, well, they want to buy these things. You know, I want to buy a snake, a very thin snake robot that I can just put through, 30 meters long. It's going to go and explore things. Unfortunately, it's just science fiction. So I'll show you why. So this is a 1.5 meter long snake here. It can support its own weight against gravity. That's quite important. So it's not lying on the floor. It has to be able to pick it up. It has to be able to pick up its own weight, very importantly. It's a 12 millimeter diameter, so that's really useful. So in this case here, you could actually drill a hole 12 millimeters, really small, my finger size, put the camera through and inspect on the other side, which is really useful. The way it works is, these different joints here, one there, for example, they are moved by cables, by wires. So you pull a wire on the top. As you pull the top wire, it bends, it twists. So we can do that, we've done it. The problem is, to do this, you require an absolutely enormous high force thing. So the amount of mechanical force, because it's so thin, you've got two wires, pulling on the wire, it's huge amounts of force. This thing here could lift up a car, but all it's doing is lifting up a 20-gram camera, very small camera on the end of this, because of the sheer amount of force in that. So to remind you again, it's a self-supporting, so it can support its own weight. Very, very difficult, very, very challenging. And in fact, we know, we've done some mathematics, we know that based upon current materials, the maximum you could do, ignoring any losses, is 3 meters. Beyond 3 meters, the material doesn't exist to make the wire strong enough to do that. So this is not the answer. It's fine for quite small things, quite close things. It's not the answer to explore very large spaces through a thing. We need some kind of different thing, some kind of mobile robot potentially. So we've built robots that can go through small holes and can transform their shape and size. This one here is a straight robot. You drill a hole in something, you put it through, and then on the other side, as you'll see, it can transform. So a way of getting into a building, and of course it's mobile, so on the other side it can drive for potentially hundreds of different meters. So it can drive an awful long way on the other side. So here it's going through a tube here. It could be pushed through, it could be pushed through or under its own power. Then it automatically changes its shape to reconfigure and then can drive around and explore things. Works really well. We have a more advanced version. At the very beginning I showed you that video. You may remember the yellow robots. It's like this, but a more advanced version. But we're getting quite close to getting these things that are really useful. In particular, things like mine rescue, search and rescue, or inspection of difficult spaces is very useful for it. We were approached to do a specific problem of inspecting a house with this kind of technology. So a house in the UK and Europe has a certain size letterbox, quite a fixed size letterbox. The hard thing here is, it's the width, or it's the depth. Width is okay, we can make ones that wide, but it has to be quite thin so you can post it. How can you go and build a robot that can do that? So that was our challenge. You'll see here in my office I'm working hard, as I always do, of course. And outside my office is my student here who's controlling the robot. Wants to see if I'm working hard, I guess. So what he's going to do, he's going to post it through a letterbox. So it goes through flat. On the other side, it's now quite flat, it can't see much, so it arches back to get a better viewpoint, so you can see what's going on. So it's got a camera on top here, now you're quite high, you can see what's going on. But also the same mechanism can be used to climb stairs. So inside a house, you can go and you can climb stairs as well and inspect the house. Of course, it's found me working quite hard. So yeah, it can't open doors, of course, but it can go in there. So kind of applications maybe like somebody's fallen over. You don't want to break the door down, the door's locked, but you want to inspect. Maybe you want to see, is there a gas leak? Is there some kind of problem there? So you want to put it that way. So it's that kind of application you're looking towards to where you want to get access, but you don't want to break the house down. Have a quick look and then decide whether it's worth forcing entry into the house. Another example here of, again, a confined space thing. So in this case, a drone. So drill a hole, quite small, put a drone in, and the drone can then go around and do things. So see here, it unfolds, or folds up, unfolds. Going through a small hole here, for example. On the other side, it changes its shape and can fly around and explore things. But yeah. But there are, so I've mentioned about going into spaces that are quite, I guess through a set defined hole. But really in search and rescue, it's a more difficult challenge than that. So here's an example of a kind of a tsunami type problem. Anybody who's injured on the outside here, somebody walking past would have rescued them. So the challenge is to get deep inside this building to find somebody. And the other problem is that, of course, as it's collapsed, you've got debris, you might have mud, you might have bits of things. So it's not to say that you couldn't find a path in, but if I just try to drive in, my robot will collect stones, it will collect dirt in front of itself, and it just cannot go through. So we want to be able to go in there and clear a space through things that are loose, to get access to the middle. So how would you do that? We took inspiration from a mole, little mole here. Of course, moles are great diggers. They have these little front feet, and they can burrow through things. So wouldn't it be great to build a mechanical version of a mole? You see here, this is a video from MIT. Little mole is wandering around, and it's digging in couscous. So it's a very useful analogy, I guess. But you see here, it's got these big feet. It can burrow through stuff. It can dig through stuff. And here's an X-ray of what it's doing. You see its feet pushing it from the front to the side. So what it's doing is material goes from the front towards the side, making a path where you can go forward and you can clear through things. So yeah, this is our concept. A conventional kind of robot with digging feet on the front, what we're trying to do. So here's a top view. So two arms. The arms initially push forward, then they pull the debris back towards the side, carry on that sequence of things. I won't worry about the mechanics on this. What we want is we want motors inside the robot itself. We don't want motors on the outside getting covered with dirt. Inside the thing, so here we've got two motors. This is the robot body here. Inside, two motors. And also these motors want to go in the same direction, never reverse. We want to control this motion but never reverse the motors. If you reverse them, you cause fatigue, and you also cause potentially a lack of quality of what you're doing. So let's have a look at this. So here's an animation. These are the motors here, two motors here. You notice at these points they never reverse. They always go in the same direction. But by making them slightly faster or slightly slower, you can cause this tip to go through and achieve this burrowing motion. So it's quite a nice, clever way of doing it. And these are constantly going around, energy efficient and low wear, very important. So we've built one, such as this. It has to be quite high force, so it's quite big bits of metal to make it quite strong. And you'll see here it working. So we've got this stuff here to show the flow. We're moving material from the front to the back, and you can see it's being pushed over here. So it's working. It's doing what it should do from the front towards the back, making some space as you go forward. Also, it's quite high force, so we can push things quite hard. It's not designed to make mechanical effort too high, but it can push small stones, other things out of the way. So it's quite a strong, powerful thing. So about 80 newtons, 8 kilograms of weight it can push at the tip of the arm, which is quite high, quite a lot of force. One of the challenges here, of course, when you have lots of loose debris, you get interlocking, so you can't really solve that problem. But you can see here, as long as they're not too interlocked, you can push them around and you can make some space in that scenario there, so pushing them out of the way. And also putting it onto actually a mobile platform here. I won't show the whole video, but effectively we can drive through here. So by a sequence of burrowing through, we can move things out of the way. When we started this work, quite interestingly, when we were driving this manually, we found that what we did was, you move the arm, and you often also use the forward and backward motion. So you put your arm in a certain place, and you drive backwards. So it's interesting, we didn't design that way, but when you use it manually, you find yourself doing that. So you're digging, but also driving forward and backwards. And with that, we can clear a path. So you can imagine a conventional robot, even though it's quite simple, could never, ever get through that. But our robot can, by these little arms, moving things around and doing different things. So it's quite a nice way of doing things. I'm going to skip this one here. So yeah, that's the answer on that one. Let's go on to this one here. So I've given you lots of applications of robots in, I guess, like civil, that kind of environment. I want to give you one flavour of a medical application. So exploration is not just in the civil applications; it can be in many applications. So in this case, it's in robot surgery. So in robot surgery, you have a thing called laparoscopic surgery. So you want to do surgery through the smallest possible hole. So you cut a small hole, you inflate the stomach with gas to make space for tools, and then you use mechanical tools that go through here that can cut, that can grab, that can do things like that inside the body. But what you struggle with, you struggle to see what you're doing. You know, one point of viewpoint is not good enough. Ideally, you have multiple points of viewpoint. So we thought, wouldn't it be great to have robots inside here that can walk around and can inspect things? But if you put a robot here, if you just drop it in, it's got to walk on these organs, and it's quite difficult. You can imagine your intestines, it's very hard. So what we thought was, let's not try and walk over these, let's try and walk on the lining of the stomach. So although it's wet it's slimy, it's curved, it's clear obstacles, so it's quite a nice clear flat surface, which is good. But I say it's slimy, so if you can imagine sort of a bit of a flexible material that is covered in horrible slimy stuff, that really is what your stomach's like. Obviously it does lots of good things, but to hold it is pretty, not very nice. So how can we make a robot that sticks onto wet material? That's quite tough. We don't want little metal grippers. You can imagine metal grippers, you dig into the skin, very soon you'll irritate the stomach, you'll cause damage yourself. So you want a very delicate thing, but it must not fall off, it must stick on, that's the challenge. So we're inspired by biology, looking at the tree frog. So the tree frog is amazing at sticking onto wet leaves. Leaves that are wet and slimy, amazing at doing that. So we thought, wouldn't it be great to make this robot for surgery? We're not suggesting putting a frog inside your body, that'd be pretty harsh. But what we are suggesting doing is making sort of a mechanical thing that's similar to this that can go inside your body. So the first question though is, how can you, how does it stick? How does this frog have amazing ability to stick to wet material? If you look at its feet, what you find it has these things called micropillars. So very, very small features that stick up, and when it touches water, what happens is liquid goes across here and causes what they call a fluid bridge and sticks to it. So it's very effective in that sense. So we wanted to go away, we wanted to make these sticky things. These are very, very small features. So I showed you at the very beginning the scale of manufacturing from cutting metal right down to micro things. In this case, we used light etching, so laser cutting and light, very high powered light, to make very, very small features. So to point out, we made this a microstructured pattern. If you have it in your hand, you look at it, you cannot see any features. It looks completely flat, you just can't see it, it's too small. But in reality, there are these features here. So if we look through an electron microscope, we zoom in, you can see here, this is what we made, all these little things on here. And when it touches water, again you get these fluid bridges, and it sticks together, and it can stick on. So not very high forces, you get about 20 grams of stick per centimetre squared. Quite small, but still strong enough to hold a small robot to wet tissue, and quite reliably. Quite reliably. So we went away, we built a prototype robot. This of course is too big, a large scale, but it is quite complex. At the time, about 4 or 5 years ago, 6 years ago, probably one of the most advanced robots in the world for its size. It has 8 small, independently controlled motors. So inside here's a motor, here's a motor, here's a motor, here's a motor, and in and out of the page, these also have motors. So lots of independently controlled motors on that we control together. We're doing a test here with small magnets. These magnets have the same amount of stickiness as actually the foot and the wet material. So rather than testing it on animals, we're testing it in this environment, but the same principles apply in both environments. And it works. You can see it walking along here. It's sticking, it's releasing, it's wandering around on the surface. One of the things I haven't mentioned though is if you push it on, it's quite sticky. When you pull it off, it requires a large amount of force. So you put it on, you've got to really pull it off. It's designed to stay on, of course. So you need to really pull it off. So how do you do that? How do you overcome that? So again, we looked at the tree frog. What the tree frog does, it pushes its foot on, but as it pulls it off, it twists, it peels its foot off. You don't put it on and pull it off straight. You put it on and you twist. As you twist, the force massively reduces and you can get away with much lower force. So you can't see it there. You look here, what happens here is the corner here comes off first. Look at that again. This corner here comes off first. So we pull it off at an angle designed to twist the pad off. And that means it's much easier to release the force, much more energy efficient, much less likely to fall off the surface, which of course is very important. So it works. What you probably noticed though is that we're actually a long, long way off building a frog, unfortunately. This is, again, it's about 4 or 5 years ago. We want to build this, and this was our state-of-the-art thing. And in fact, this was made by one of my PhD students, spending weeks with pairs of tweezers, very small files, trying to get it to assemble. It was just such a terrible process. So in fact, what we used this as a case study, went to the UK government and said, this is not good enough. We need to be able to build amazing robots at small scale. And we have these challenges here. So we want to be able to build robots with high complexity. So rather than 8, let's give it 300 different motors. Bear in mind here, we're not saying complexity for the sake of it. We're not saying have lots of motors for no reason. We're saying if there's a reason to have 300 motors, we want to be able to make them in this system here. We want to have miniaturization. How can we make it small? We want to have 3D integration. So right now it's made by a motor, a bit of material joined together. We want to be able to use the casing of the motor as part of the structure to make it all integrated. So imagine biology. Biology, everything has dual purposes. We don't want a standalone motor, a standalone mechanical structure. We want it to be integrated, therefore more efficient. Likewise, we have, let's go back, minimal assembly. So let's make it in one go, nobody assembling it. We press go, we press print, out pops a walking, functioning robot. That's what we're trying to do. So we have this big facility, so very large machines to manufacture quite small parts. I think we're quite short of time, so I'll skip the video there. I'll give you a couple of examples of what we're doing in terms of manufacturing though. So the first thing we're trying to do is make small walking robots. So we have a thing here, and you'll see it's designed here, small walking robot. So we have, on the left side and the right side, one motor powers, so this one motor here powers 3 legs. You have them on the left, on the right, you do them out of sequence and you can go forward or backwards, that kind of thing. We want to be able to make this without any assembly. Nobody goes there, takes a pin, takes a leg, joins together. We want to print it, 3D print it in one go. And you'll see here we've done that. So here we are, we're making it here. So we have a bottom half, a top half, and 2 motors, and that's it. So the whole bottom half, all of these legs, all of these joints, printed in one go. Nobody's assembled it. It's designed to work in one go. So all these legs here, gears, linkages, printed in a single go, working really, really well. So that's great, we can do that. I mentioned before though, you have a bottom half, a top half, and 2 motors. Still some assembly, although you're assembling big parts. We want to be able to actually be able to have it printed in one go with the motors in situ. So I'll show you a video of this now. We have robots that can do 3D printing. So these things here are the printing. If you're doing that, you can do things like rotate gravity. So if you're 3D printing, normally you're limited by gravity causing things to sag. We have 2 robots so we can print, and as we print, we can rotate them. So gravity is no longer a problem, we can change that. We can print to make things stronger. So print on curves, make it stronger that way. And we can also print around things. So I'll show you a video here. We've got a motor and a propeller, and we're trying to make an aircraft in one go. Take the motor, propeller, let's print the aircraft around the propeller. So we show there that we can print the aircraft. We still have not yet made a functioning aircraft, so it's work in progress. I think it's always fine to embrace these things, it's okay. The challenge here really is that we can take an aircraft structure. This is normally made in quite low material weight sort of things. We're using plastics that are much higher, so we have to make a much more advanced aircraft structure. in order that it flies. That's what we're doing right now. So a better aircraft structure, a more powerful motor, but in this sense, success, we can print around objects, we just can't build great planes as yet. Work in progress. And the last thing I'm going to mention is this vision of what we're trying to do. We're trying to print things around things. I've shown you the little leg walker. We have an aspiration to do a much more complicated thing. We're calling it Leonardo's lion. So Leonardo da Vinci built a lion. We don't want to duplicate what he did. What we're saying is, if he was alive now and was to try and use mechanical things, what would he do? So we want to make the most advanced, most complicated 3D printed thing in one go. So the idea is you print out a lion, effectively. We have the world's largest 3D printer in Leeds, so we can print out, this multi-material printer, we can print out structures that are 1 meter by 1 meter by 0.5, very large structures. We want to print out a fully working legged thing. We attach one motor to it and done, it walks away. So you show you an animation here. It's quite complicated. We know this is actually a simulation. It's a dead simulation working out the forces, so it can walk. Normally you can't do this. Normally you shouldn't be able to get away with having one motor to make a thing walk, but because it's got big feet, you can get away with it. So we know we can do this. We want to print it. The problem is that to print this costs about 40,000 UK pounds, very large bits of material on a 3D printer. If we print it, if it doesn't work, it goes straight in the bin. There's no fixing it. So we have to be really, really sure that when we print it, it works out okay. But anyway, that's the next thing we're going to do, make that. And also, we're also into quadrupeds. So this is coming up. We're going to be going much more towards exploration robots with quadrupeds. These are commercial ones we're going to buy, and we're going to start modifying them. They're amazing bits of kit. This one here is from Switzerland, and it's about 250,000 UK pounds. Very, very expensive, fully working robots. These ones here are from China. Each one costs 10,000 US dollars. So a massive difference. Of course, it's more expenses on, but clearly China again has shown they're amazing at making things at very low cost. We're going to buy these and modify them. Okay, so that's the end of my talk. I guess just to summarise what we've talked about robots exploring in different environments. Very important you consider the environment, open space, confined space, or access problems, and likewise making them the big issue. How can you make amazing robots that really function really well? So thanks a lot for your time. Thank you.
Thank you, sir. It was a nice session. We have some queries from the audience end. We have also collected some questions. I would like to read some questions which the audience have put. First question, the percentage of job opportunities in the field of robotics in coming days. What would be the percentage of job opportunities?
Just a second, sorry.
What would be the percentage of job opportunities in the field of robotics?
The percentage opportunities. Yes, I think there'd be massive opportunity in robotics, so I think it's a massive growth area. And the percentage opportunities, I guess it's got, you're saying how many jobs will be robotic jobs opposed to other jobs. I guess in the future it's going to be a lot of things robot jobs. I reckon high technology, probably half the jobs will be high technology. There is lots of concern about this job issue. How do we ensure that people who are doing manual jobs still have work? It's obviously quite an important thing. So our view really is that you don't hide from this issue, you actually embrace it and you investigate and you work out what the issues are here. But there's definitely a massive question there. And I guess the big question is, if robots, as they should do, are doing lots and lots more jobs, what do those people do who now have less job to do? Do they have no work? Do they have income for doing nothing? Of course, to me, the answer is retraining. Retraining to many different areas, but we have to be sure and measure these things. But I don't have a negative view. I think clearly robots doing things that are useful, helping us to do less things that are less nasty is a really good thing. We have to just make sure we give a lot of thought to making sure that robots don't do bad things. And also in particular, there's a lot of concern around robots helping the wealthy. So you're wealthy, you can afford a robot. If you're not wealthy, it puts you out of work. There's a massive concern about this disparity. So we need to make sure, again, I'm not concerned, but what I do believe in is giving a lot of thought and making sure these things that are concerns, genuine concerns, never come true.
Sir, next question. By accident, if a child has fallen down in a manhole, how to rectify whether the child is alive or not? Or is it possible to survive the child?
Okay, so yes, so robots can get access to difficult spaces, absolutely. The challenge quite often is, though, how long did it take to get the robot there? So I did a lot of work previously in the area of search and rescue robots, which of course are very useful. But so the problem really is in terms of, again, the business case, sorry to talk about cold, hard business cases, financially, how many would you need to have across India, across the world, to be ready for finding people? It's really hard. So for me, we did also work on robots to inspect, repair, and maintain cities. So robots cleaning the roads, getting rid of rubbish. The business case, again, it sounds quite hard to talk this way, but the business case really is these robots can be retasked. So they're away somewhere doing a drain repair, someone's fallen down, you can retask that robot to rescue someone. That's the way to do it. I think if you try to make a specialized robot for that task, it's just really hard. How many would you need? 1 million across the country? How many would be used? It's very difficult. Of course, every life's very important, but it's very hard to do that. In terms of technology, you can access places, you can use things like thermal cameras, sound in particular, you can use robots to get through debris, to inspect things, so it's all feasible. Of course, batteries is quite difficult, and really the challenge is around about how consistent or how well known is the challenge. If you go into an environment of unknown size, unknown objects, unknown distance, that's really tough. If you can know a bit about what you're trying to do, maybe you have 3 or 4 different robots with different skills, and maybe they could just about do the task. So it can be done, but there are many financial and technical challenges as well.
Next question. Do the robots have a self-defense mechanism? Example, if a robot come across a creature inside a tunnel.
So self-defense against robots or against people or against?
Yes, creature inside a tunnel.
Okay. So yeah, so they certainly could have. So I think in terms of the rules of robotics, of course robots should never kill or harm someone. There also are rules that robots should also maintain its health, as long as it doesn't affect any other things. So it certainly can have a self-defense mechanism. It shouldn't harm a person doing that, but it should certainly be able to do things. And there are some work going on with drones, for example, drones designed to evade being attacked by other things. I mean, of course, you could argue, why is that drone being attacked in the first place? But there are some people working in that area. So the manufacturers of drones are quite interested in drones being able to avoid, I guess, avoiding birds for its own protection, but also avoiding being taken down by other drones, that kind of thing. There is work in that area.
One more question, sir. A lot of challenges were found during the Fukushima Daiichi disaster in 2011, tsunami in Japan. How can robotics change and improve decommissioning of nuclear reactors in the future?
Okay. So yeah, the nuclear case is a very specialised case. So robots absolutely can do that. So in the UK, one of the biggest problems in the UK is decommissioning of a nuclear power station. It's one of the oldest nuclear powers in the world. And we have nuclear power stations that are being decommissioned now. The problem is that they were built 50 years ago, 60 years ago, and no one's really sure what's in there. There's water that's contaminated, all kinds of things. So robots can do this, and they are doing this. It's a massive thing going forward. The challenges are the nuclear environment. It damages plastic, electronics, and there are really 2 schools of thought on this. The first one is, we'll build robots that can withstand nuclear environments. They're very expensive, very complex, but they can last for long periods of time in nuclear environments. The other school of thought is, let's just buy a cheap robot. It's going to break, but we'll tolerate that. So for example, a commercial drone, we'll just buy it for 1,000 UK pounds, quite cheap. We'll put it in there, it'll last for half an hour, and it will die. We'll buy another one. So The first case, a fully radiation-proof robot, might cost £1 million UK pounds. A drone to be disposed is perhaps 1,000. So you can have an awful lot of drones that fail for the cost of one that doesn't fail. Of course, the downside is every time a robot fails in a nuclear environment, it's more rubbish, more nuclear waste to be removed. So there's definitely pros and cons there. But right now, the trend is mostly around these robots that you just throw in there, disposable, do a job, and later on, we'll worry about how we get rid of them.
Thank you, sir.